Problem posed here is to find the area of one petal of the polar curve r equals cosine of 2 theta. So clearly we have 4 petals, we only want one of them. So some people might say, well, why not just integrate from 0 to 2 pi and divide the answer by 4? Well, that might work. We would have to double check and make sure that theta going from 0 to 2 pi is actually going to trace out the curve once. And if the answer is yes, then probably that's fine, based on symmetry, that we can just go from 0 to 2 pi and then divide the whole answer by 4. And yeah, that'll work on this particular one. If we have an odd number of petals, however, that's not going to work. So I'm going to try to keep this a little bit more general, and I want to think about, well, where does this start? Okay, and when I say start, I always think about theta equals 0. We know that theta equals 0 is right here. And when theta equals 0, r equals cosine of 0, or 1. So this is the starting point. And as theta gets bigger, right, we're rotating counterclockwise. So we're following this curve in this direction. And now my question is, when do we finish tracing out the top half of this petal? Well, it's when we hit the pole, right? When we hit this point right here, we know that we have finished tracing out the top half of that right petal. So what is that theta value? Well, it's the first theta value bigger than 0 such that r equals 0. So let's just set r equal to 0 and solve for theta. So we know that the cosine of an angle equals 0 when that angle equals pi over 2. That's the first angle that's bigger than 0, whose cosine is 0. And so if 2 theta equals pi over 2, then 1 theta equals pi over 4. All right, so that seems to jive, right? We've got that line right there is the tangent line to the pole, or at the pole rather, and it looks like it's at theta equals pi over 4. And that's when we get to the pole first, starting at theta equals 0. So what I'm going to do is I'm going to integrate from 0 to pi over 4. And that's going to find this area bounded by the curve. And then I'm going to realize that that's just half of the area I'm looking for, so I'm going to double it. So 1/2 the petal is going to be 1/2 the integral from 0 to pi over 2 of r squared d theta. Okay, now be careful here. This 1/2 doesn't exist because I'm finding 1/2 the petal. This 1/2 exists because that's part of the area formula for polar curves, right? Half r squared times d theta. Okay, so that's half of my answer. So I want to make sure I double this. That's pretty convenient because now, oh, wait a second. Why did I put 2 here? I think because I was looking at the 2 right here. I meant 4. Oops. That was going to be frustrating later on if I hadn't caught that. So yeah, we're going from theta equals 0 to theta equals pi over 4. And this 2 times 1/2 is nice because that means that we don't have that coefficient anymore. They cancel each other out. So we've got the integral from 0 to pi over 4 of cosine squared of something. And we know how to integrate that. We integrate that using the power reducing identity, which is 1 plus the cosine of the double of the angle, so 4 theta, divided by 2 d theta. All right, so then we just work it out. We take that 1/2, pull it out front. We've got 1, and we've got cosine of 4 theta, d theta, still going from 0 to pi over 4. And, oh, running out of space. I guess I'll use my right margin. So that's going to make it ready to integrate, unless you want to do some u substitution. I like to do this u substitution in my head, though. 1 times d theta integrates to theta, and then instead of messing with u equals 4 theta, I'm just going to remember that I have to unchain rule this. So divide by 4, cosine anti-differentiates to sine, and the argument never changes. We'll evaluate that at pi over 4, and we'll evaluate that at 0. So we've got 1/2 times pi over 4 plus 1/4 sine of 4 times pi over 4 is just 4 times pi. I'm sorry, 4, it's just pi, excuse me. And then we'll also do the same thing with 0, and we'll get 0 plus 1/4 sine of 0. All right, so lots of this goes away, right? Because the sine of pi is 0, and sine of 0 is 0, and 0 is also 0. So the only thing that's non-zero here is this pi over 4. So our answer looks like is pi over 8. The area of one full petal on this polar curve. Let me see if I can do a little bit more explanation here for those who might need it. This 2 right here is to account for the bottom half of the petal. We've got 2 different halves of the petal, whereas this 1/2 is just part of the formula. All right. Hopefully that made some sense.